there was a student in my group, master's, and then he became PhD student with Anton Kokon, who was postdoc in my group. Now he's at Chalmers permanent. And Munoz, he was a postdoc in my group. Now he's in Madrid, Spain. We're still working together. But it's a project that took almost 4 years of work to get done. We started in my group and eventually finished in Anton's group. And then the long paper is how to classify and reconstruct optical quantum states with deep neural networks. The density matrix reconstruction initially from the data, remember Reiner-Blatt and others on ion traps, to get the density matrix will take them a huge amount of CPU. And then over time, instead of taking weeks, it was taking days, and then hours, and then minutes. And then the idea is to do this faster and faster and faster because the tomography on real time can be very time consuming. So therefore, these deep neural networks can be very effective for quantum state characterization. This is quantum state tomography using generative adversarial networks. They need to use these generative for quantum state reconstruction. It's a faster reconstruction, measure in the number of iterations. You can reconstruct mixed states with much fewer data points and reconstruct states from noisy experimental data with arbitrary measurement, because the problem with this pattern recognition is that as soon as you have your state like squeeze here or squeeze there, then the program gets confused. So you need to train the data to allow all kind of errors. So it took some time to do this properly. And it can handle different kind of noise because it was trained for different kinds of noise. And can also do, in some cases, single-shot reconstructions. So therefore, the typical approach is you have a parameter, it could be initial conditions, the model, and then there's a data. Some people do the inverse scattering problem, or the inverse problem. You have the data and try to reconstruct the parameters. You can do it inverse in this case or forward here. But right now, we're trying to learn from the data. So therefore, you put a whole bunch of data, try to develop an algorithm, and make predictions. And then in this case, the measurements are made, their input and the initial vector here. It is a hidden layer, 2, 3, 4, n number of layers, output layer, and from there to get density matrix, the fidelity, the measure of entanglement, Wigner functions, negativity, concurrence, et cetera, et cetera. So that's the goal. It's a challenging task. We're using a different approach than other group, which is these generative adversarial networks. They're two dueling. They're competing, a generator and a discriminator that learns models from the data. And then we put some neural network layer to enable conversion of the output into a physical density matrix. So therefore, exactly, so they're training each other on data using standard gradient-based methods. These quantum state tomography generative adversarial networks construct optical quantum state with high fidelity using orders of magnitude fewer iterative steps, less data than both accelerated projected gradient-based methods and iterative maximum likelihood estimation. So the reason why the long paper is long is because we had to test all kinds of things to make sure this was working fine. And in some cases, if he has been properly trained on similar quantum states, he can do it in one shot, but this is if you happen to be lucky. And then, so the data is here. There are some measurement operators. You input at the initial layer here. There are 1, 2, 3, n number of layers in between on the output layer to get, the generator is going to generate density matrix, expectation values, consider noise models, Gaussian photon loss, etc. The trace has to be normalized. You reconstruct the data. And the neural network, based on some data, the discriminator is going to accept it or not. It's going to reject it or not, because they are in an adversarial competing approach to each other. And then there are these convolutional neural networks to classify them either into these Fock states, coherent states, thermal states, cat states, binomial, num states. These GKP are often used for quantum error correction. Is the Gottesman, Kitaev, Preskill states. How do they look like? So there are many classes of optical quantum states, it's easier to see this visual pattern with the Wigner function. In this case, will be the Fock state, coherent state, thermal state. Actually, if I do this one here, it's coherent, and if I do like this, it looks like squeezed. The thermal, random, as you can see, looks pretty random. Num state, I mean, specific combination of Fock states, binomial state, it looks very pretty, symmetric, but often in the data, if there is anything like this, looks squeezed or stretched. It doesn't look as pretty in the data. The cat state, the GKP state, but you can see then the Hinton plus for the density matrix here for the Fock states in the case of NN, or the coherent state spread, thermal state, random one a bit all over. Num state are of this form as opposed to this one here, so there are more N states involved. Binomial like this, cat states, and this one here. So there are many class of optical quantum states, and you would like the system to be able to discriminate and figure out which one is which in the system. So therefore, to characterize them, you need to look at the density matrix, and then those are either a Wigner function or the Husimi Q function where there is this beta here, and depending on the value of, this is Q beta 0, but could be Q beta 2, Q beta 3, there are the higher order states, higher order generalized Q functions. One of them will be the Wigner one, but there are more general versions of it. Already we talked about this. But the data can be very noisy, so you need to add Gaussian noise, more Gaussian noise. This is very messy. Spam, there's a definition for this. I'll tell you in a moment in the next slide. Affine, photon losses, mixed state. Spam means state preparation and measurement noise, which means any other type of systematic noise, which is spam is a good abbreviation because it's like a spam noise. You can get the thermal state, the distorted binomial state, and the distorted numerically optimized for error correction superposition of Fock state. So this is a superposition of Fock state which are well optimized for error correction. We were using another one, the 2-4 photon combination is a special case of num state. Introduce noise in the models. Exactly, so these, you need to train them to learn patterns in data that have noise. Otherwise, the machine gets like this and I say, I don't know what to do because it doesn't match the ideal case. And this is an example. This is from data from Chalmers. This is data, noisy experimental data close to binomial state here. There are better ones, but this slide is old. And then, so in this case, replacing the measurement operator for displacement parity. And the summary of this part, it is possible to use these adversarial networks and deep neural networks for quantum state characterization to save you a lot of time to characterize the states. It's a technique that uses generative adversarial network for quantum state reconstruction. It's faster in the number of iterations, reconstructing mixed state with much fewer data points, and it can handle noisy data, different kind of noise, and if you're lucky, you get single shot reconstructions. It has been properly pre-trained in those data here. So now let's look at topological quantum phase transition with unsupervised learning. So this is done in collaboration with Yang-Min Che, Clemens Gneiting, and Tao Liu. And so therefore, so there is here, there is quantum enhanced machine learning, but we are not working on this. So other people are doing this. So we're doing it, we're using classical machine learning applied to quantum problem. We haven't found cases where the quantum machine learning is really helpful. There might be, but we're not doing this. So therefore, one of the problems we want to do is to identify topological quantum phase and phase transitions in quantum many-body physics, and then exactly the conventional phase transition, which is the Landau paradigm, is driven by thermal or quantum fluctuation like melting, evaporation, spin fluctuation in ferromagnetic,